Greetings, everyone, and welcome to the Oregon State Engineering Virtual Symposium. I'm so glad that you could be with us today. We have an incredible event planned for you this afternoon, including a panel of current Oregon State engineering students who are working on groundbreaking design projects, and of course, a live Q&A with astronaut Ellen Ochoa. I know that many of you with us today are high school students who are trying to decide where you want to go to college and what you might want to study, and I hope that today's event helps inspire you. My name is Lauren Lippman, and my pronouns are she, her, hers, and I'm studying chemical engineering here at OSU. I'm also a College of Engineering student ambassador, and I'm very excited to be the host and moderator of today's event. Before we get started, I just have a few quick things to remind you of. First, if you experience any technical issues, you can log out and log back in using that same link that was first sent to you, and hopefully that will resolve some of your connectivity problems. Also, any high school students who have registered for today's event have also been entered into a raffle to receive a prize bag from OSU full of Oregon State engineering swag, like a Nalgene water bottle and a mug. We've drawn 5 total winners at random, and you'll receive an email at the end of today's event telling you more about how to receive your prize. Lastly, you have a Q&A function at the bottom of your screen, and for both that live panel with the OSU students and that Q&A with astronaut Ellen Ochoa, you can use that Q&A feature to send in questions. They'll come straight to me, and then I'll ask as many of them as I can within the allotted time. Now, let's get started. First, I'll give you an overview of what you can expect today. We have a live panel of 5 Oregon State engineering student design projects, and we'll be hearing from Scott Ashford, the Carney Dean of Engineering, and then we'll go into that live Q&A with Dr. Ochoa. We'll conclude with some information on additional resources you can access, and don't forget to send in questions the whole time. Before we begin that first panel, I'll just give you a quick overview of the College of Engineering. The College of Engineering really is an incredible community, and I'm very proud to be a part of it. So here are just a few quick facts. We are the 10th largest College of Engineering in the country. We have the number 4 robotics program in the nation and the number 9 best online engineering program in the nation. We're also number 3 among public R1 universities for the percentage of faculty who are women. All of the faculty, staff, and leadership are really committed to student success, including the delivery of distance learning during this current situation. And now facts and figures are, I can tell you that the faculty, the staff, student leaders, they're all incredibly dedicated to student success and our well-being. Speaking of amazing people, it is now my pleasure to introduce the members of the Student Design Panel. Each Oregon State engineering student on the panel has been working on a design project that's focused on tackling solutions to real-world problems. We'll have each panelist share briefly about their project, and then we'll open it up to you, the audience, to ask some questions. First up, we have Cameron Bennett. Cameron, will you please introduce yourself to the audience and then tell us why you decided to become an Oregon State engineer?
Yeah, hi Lauren. Thanks for having me. My name is Cameron Bennett. I'm from Portland, Oregon, and I'm a civil engineering major here at Oregon State. I originally became a Beaver because of the fantastic value that the engineering program provides for the in-state tuition that you pay. Back to you.
Thank you, Cameron. Next up, we have Amy Caldwell.
Thank you, Lauren. Hello, everyone. My name is Amy Caldwell, and I'm a mechanical engineering major originally from Portland, Oregon. I joined Oregon State Engineering for its aerospace program. Back to you, Lauren.
Thank you so much, Amy. Now we have Siena, she.
Hi, everyone. My name is Siena. My pronouns are she, her, hers. I am currently a third-year electrical and computer engineering student. I was originally from China, but I have been living in Portland for almost 10 years now. I chose Oregon State just because it simply has the best engineering program in the state. Thank you. Back to you, Lauren.
Thank you, Siena. Now we have Austin Warren.
Thank you, Lauren. My name is Austin Warren. I'm originally from Gig Harbor, Washington. I'm a nuclear engineering major here at Oregon State, and I came to Oregon State University because of the nuclear engineering program. Back to you, Lauren.
Thank you, Austin, and I'm actually your final panelist, and I'll be representing environmental engineering. I'm from Phoenix, Arizona, and part of why I came to OSU was for the change of pace, but it was really the community for women in engineering that hooked me and got me to be an OSU engineer. So now that you know a little bit about each of us, we'll each share a little bit about our projects. So each panelist will share their project and some visuals with you, and we'll start with Cameron.
All right, thanks Lauren. Super excited to share my project with y'all today. I'm going to talk about the capstone design project that a bunch of the civil engineering students are working on this term. We're doing a redesign of Hoover Elementary School, which many of you actually might have attended in North Corvallis. It's a fantastic project for us because it's right around the corner from us here at school. So we can go on site and look at current conditions, look at how people are using the facilities. On the project, we have a handful of disciplines. On our team, we've got a water resource specialist, 2 transportation specialists, and 1 structures specialist. I am working on the offsite transportation design and planning. Most specifically, I'm looking at the intersections that border the school. For part of my project, I looked at the entire transportation system in the area surrounding the school and looked at where there might be some opportunities to link existing infrastructure with the school for this project. I noticed a gap in the multimodal system, so in the system that people use for things other than cars, between Dr. Martin Luther King Park and Hoover Elementary School's site. We see a multi-use path that gets almost to the school, but not quite there. And so for my design process, I looked to see if it was possible to design a multi-use path to connect the school to the park and to the greater community. To do so, I made sure that dropping lanes on Walnut Boulevard, which is the major street connecting the 2 spots, was feasible in order to keep the intersections in the area functioning. We used a modeling software called Synchro to do so, put in the existing traffic volumes, scaled them to the future, and looked at the impact of the school project on them. And what we found at the end of the day was that it was feasible to reduce the number of lanes on the street and insert a large multi-use path and bike lanes separated from traffic that would be safe for the school children to use to get to school. So overall, very fantastic project, and the opportunity to put together some engineering design drawings at the end of it that comply with all the regulations that the state's transportation department and other national transportation guidelines recommend, as well as all the requirements for the project. And yeah, here you're seeing the entryway to the school, as well as the design for the streetway at the intersection of Walnut and Aspen. I am super happy to be a civil engineer. You get the privilege of working on environments that people use every day, and I hope that strikes a chord with some of you. Happy to answer any questions you have about transportation engineering, the School of Civil and Construction Engineering, or public infrastructure in general. Back to you, Lauren.
Thank you so much, Cameron. Next up, we have Amy.
Thank you, Lauren, and I'm really excited today to be able to share with all of you about Oregon State's phenomenal rocketry program. So my design project this year impacts the safety of all of the students who are or will be in 1 or more of our 7 rocketry teams here at Oregon State University, as well as make some of our parachute ejection systems safer. This project of which I speak is an entry for a rocketry competition called NASA USLI, which stands for the NASA University Student Launch Initiative. This competition is meant to mimic a NASA project lifecycle from start to end. And while the challenge changes every year, this year we had to complete 2 separate challenges. First, we were tasked to call an altitude, which is how high the rocket will go, all the way back at the start of November, and then fly as close as possible to that altitude at competition, which would have been in the first week of April. Second, we had to build some kind of robot to navigate over the Alabama fields to 1 of 5 3-foot diameter circles, and collect at least 10 milliliters of lunar ice, store it in the robot, and then transport that ice out of the circle and 10 feet in any direction. To accomplish this, my team split into 3 engineering subteams: aerodynamics and recovery, structures and propulsion, and payload. My subteam is aerodynamics and recovery, and what that means is that we focus on homing in on that altitude and also bringing the rocket and the payload safely back to the ground. There are 3 areas of specialization on my subteam. The first focuses on designing and manufacturing the recovery system layout, which you see here on the left-hand side, to ensure that we meet NASA requirements and then also come down safely. The second, which you see on the right, is our active air brake system, Beeves 2.0, which senses how fast the rocket is going, calculates the projected altitude in real time, and then sticks out some fins accordingly to increase the amount of drag and lower the overall altitude. The third specialization is what I specialize in, which is parachute deployment and developing safer methods with which to deploy the parachutes. This means that I select the rocket's barometric altimeters and set them accordingly, calculate the size of and test our black powder deployment charges, and then also this year I've been working on developing a completely black powderless CO2 parachute ejection system, which is seen on the left-hand side, which cost and weight effectively eliminates the need for black powder, which is always a safety hazard. I've also developed a system on the right-hand side called Embers, which ensures that our largest black powder charges will be detonated before the rocket lands by the altimeters pulling a plastic pull tab as they pull away from the rest of the rocket, which releases a spring which pushes the leads of the black powder charge against the leads that are connected to a battery via a switch. This ensures safer deployment and recovery because if the smaller charges fail to deploy the parachutes, then the bigger charges will act like they usually would. But if the small charges work, then the larger charges will be detonated inside the airframe while it is still descending, which protects our parachutes and the people recovering the rocket by guaranteeing elimination of the charge during descent. Thank you all so very much for your time, and back to you, Lauren.
Thank you so much, Amy. Now we have Siena.
Thank you, Lauren. I'm very excited to be talking about my project with everybody here today. So this project was for junior design, which is a class that spans over 2 terms during our junior year, and is aimed to have the students to get hands-on experiences. So the project's name is Flexor Sketch, because just like an Etch-a-Sketch, it draws whenever the user flexes their muscle and rotates their wrist. The Flexor Sketch is a 2-axis robotic arm, which basically means that it has 2 joints, the shoulder and the elbow. So this project was a very brief introduction to working with EMG or electromyography sensors, which is a type of sensor that's often used in prosthetic technology field. So right here, you can see an early prototype of the project, and here is the finished product. So like what I have just mentioned, the user can control the movement of the arm by flexing their muscle and rotating their wrist. To do so, 2 sensors are used. An EMG, or again, an electromyography sensor that detects muscle movements and transmits it as an electric signal to a microcontroller, which you can think of it as a tiny little computer. So for this project, we chose to use an Arduino. The other sensor that we use for this project is an accelerometer, which detects the acceleration in the X, Y, and Z axis. The robotic arm could also move based on the MATLAB graphical user interface, which lets the user to enter an X and Y coordinates on the drawing surface. The user could also specify a G-code command, which is a set of predefined movements for the robotic arm. Each point on the drawing surface is mapped out as tiny little grids. So to move from one point to the other, it's like finding the hypotenuse of tiny triangles over and over again, as you can see here on the in the upper right-hand corner. So the next step for this project would be a working prosthetic hand for below elbow amputees that will allow them to control each individual fingers by having a band of EMG sensors around their arm to detect muscle movements. I hope everybody enjoyed my presentation. Feel free to ask me any questions later on. Thank you. Back to you, Lauren.
Thank you, Siena. And now we have Austin.
Thank you, Lauren. I am very excited to share my presentation with all of you today. I always love the opportunity to share about nuclear engineering. On this slide in front of you, you can see a render of the Henry prototype built and tested here at Oregon State University. The Henry system is designed to inject helium-3 gas into this long tube into the core of the treat reactor at the Idaho National Laboratory. The treat reactor uses transients, or short bursts of high power, to test nuclear fuels and other materials under accident-like conditions. This is very important for the safety of both older model nuclear reactors and the next generation of nuclear reactors, to be able to know what your materials and fuels are going to do if an accident were to happen. Treat currently cannot test all the accidents that they want to
Hey,
test.
Austin?
Yes.
I'm having trouble seeing your slides.
Oh dear.
No worries.
Thank you for that. Let's try that again. So now you can all see the Henry prototype. Yes? All right. So, like I was saying before you could see pictures, the helium-3 is injected into this tube, which will be in the middle of the treat core. And that helium-3 will grab up a bunch of neutrons and help the treat reactor shape transients in a better way to model different accidents that they want to model. This is very important to make sure that fuels are tested under all accident conditions that we have. One of the problems with helium-3 is that it spits out a proton whenever it absorbs a neutron. And a proton, being a charged particle, can deposit a lot of energy into the gas around it. And this energy heats up the gas and then lowers the density. This density change can significantly change how the system will need to be controlled and affect reactor control in the treat system. So it's very important to understand exactly how this density of the helium will change during use of the Henry system. To do that, my senior project is going to use xenon-135 to test these density changes. Xenon-135 is a very strong neutron absorber, similar to helium-3, but because helium-3 is very expensive, we can't use that to test its own effects. So we're going to use xenon-135, which we can make ourselves using the Oregon State Trigger Reactor. Here on your screen is a plot of different levels of xenon-135 that we can produce using xenon-134 bombarded by neutrons in the reactor. This calculations that we did early on in the project were very important to show that there's some chance of us actually being able to use xenon-135 in amounts necessary to do experiments. On this slide, you can see a model of our a little test capsule full of xenon in the OSU trigger reactor in a reactor physics code. This is a beam port, and neutrons will come down this beam port and hit this capsule. And using this code, we can model what's going to happen to our experiment, and so we have a good idea of whether it'll work or not, or what we need to change to get it to work. Hopefully you've enjoyed this presentation. I always love sharing about nuclear engineering. Please ask questions, and back to you, Lauren.
Thank you, Austin. Now I'll share about my project within environmental engineering. It's actually about biochar columns and their ability to remove antibiotic-resistant bacteria from stormwater. The World Health Organization believes that if we don't do anything to stop it, then by the year 2050, antimicrobial resistance will be killing more people than cancer globally. Water is a really great way for antibiotic-resistant bacteria to grow and spread, so we're always looking for a way to inexpensively but still effectively treat our water. The solution we're looking into right now is called biochar. It's essentially some sort of biomass that's gone through pyrolysis and out comes like a charcoal type substance, and it's very porous. And since it has such a large surface area, it's able to absorb a lot of water and nutrients, which is why it's used as a soil amendment right now. But what we're studying is actually its ability to absorb contaminants like antibiotic-resistant bacteria. So we started a column test, and we filled one column full of soil, one with soil and biochar in a mixture similar to what you'd see in a soil amendment, and one with just biochar. We go to Avery Park here in Corvallis to collect stormwater, and then we spike it full of E. coli, and we run that dirty water through the columns, testing both what we put in and what comes out of each of the individual columns. We do this using auger plates. So each of those plates essentially has bacteria food on it, and each of the dots that you see is a colony of bacteria. And so the first row is from our soil column, the middle row from the soil and biochar column, and the final row from our biochar column. So you can see that the soil water was definitely dirtier than the biochar water, which is exactly what we'd anticipate. And it turns out that each of the media were pretty great at cleaning our water, which is great news. So now I have a whole nother year to run tests on different kinds of biochar and different strains of antibiotic-resistant bacteria to see if we can make a recommendation in the future as to how you should use biochar most effectively. So now that you know a little bit about each of our projects, it's time to open up the panel to questions from all of you. So feel free to use that Q&A function. This is a great chance to hear firsthand from Oregon State engineering students. As people start sending in their questions, I'll lead off with one. Could each panelist briefly talk about what led you to decide to work on your project specifically? We'll start with Cameron.
Yeah, thanks for the question, Lauren. Because civil engineering projects are super intensive with the amount of data and regulations and coordination with stakeholders that they require, there's typically only 1 or 2 projects to choose from for capstone students in civil engineering. And this year, the Hoover Elementary School project happened to be the project option that had a transportation component in it. And through my internships, I've really developed a focus and a love for transportation. And so I decided to work on the Hoover project so that I could get some more experience in that realm. Back to you, Lauren.
Thank you, Cameron. Now, Amy.
Thank you, Lauren. I originally selected my current design project because I've been interested in engineering within aerospace for quite a while now. I started within our aerospace club here when I was a freshman, and then I had chances to work with black powder and CO2 different devices throughout my 3 years before becoming a senior. And therefore, because also I wanted to work for NASA and I've been very fortunate to be able to work with them for the last 3 years as well, I decided to work with NASA USLI and focus on black powder and CO2 parachute ejection. Back to you, Lauren.
Thanks, Amy. Over to you, Sienna.
Thank you. So I decided to work on this project because I have always wanted to do something that's related to prosthetics. And once I had this, once I was in this class, which I can choose basically any kind of project that I want, of course, yeah, this is the one that I chose. Yep. Back to you, Lauren.
Thank you, Sienna. Now go for it, Austin.
Thank you, Lauren. I chose my project. I actually have been working on the Henry project as a whole for almost 2 years, and I asked my professor if he had any related projects for a senior design project, and he came up with the Xenon project that we're working on now. Thank you. Back to you, Lauren.
Thanks, Austin. I actually started my project because I met my professor at an event that the Society of Women Engineers put on called Faculty, where you have tea with faculty members. And then I got to go on a tour of this faculty member's lab and meet her lab group, and everything just fell into place from there. Now it is time for our first audience question. Did you all work individually on this project or with a team? And then if you did work with a team, how did you organize it or how did you collaborate? We'll start with Cameron.
Yeah, this question's super interesting, especially for those of us that are working on these projects through this year. So civil engineers do their capstone project over 2 terms, which means that we started in January and we're continuing this project through June. And that means that, last term we had all of our interactions in person up until it was time to stay at home for the pandemic here. And our interactions have been a little bit different. And so like I mentioned, I'm in a group of 4 for this project. And we did weekly meetings in person, and we met in class, of course, to work on this project, as it is kind of a class organized capstone rather than one that's kind of organized individually. But now that we're working remotely, it's been a little bit more challenging to work as a group, but largely the systems that we set up are still in place, kind of exchanging documents using the school drives, using Google Drive, and using just a group text to stay in touch. And we do weekly video calls as well, just to see each other's faces and communicate a little bit more clearly. Back to you, Lauren.
Thanks, Cameron. Next up, Amy.
Thank you, Lauren. So I'm on a team called NASA USLI, and that is a team of 30 different students from a whole range of majors, primarily in engineering. So we're looking at ECE, CS. We are also looking at mechanical engineers, but we also have people from human developmental and family science and education majors and microbiologists with us as well, and also a whole host of different grades. So we have freshmen up through graduate students working on this project. With my particular project, though, working on black powder and CO2, I'm the only person working on that particular section. Back to you, Lauren.
Thanks, Amy. Next up, we have Sienna.
All right, so I did not work on this project just by myself. I could probably never do that. I was in a team of 4, including myself. My responsibility was working with the sensors, and we also have people that focus on the 3D modeling. Some people focus on only the programming aspect of the project, and it helps a lot because we're basically in every single classes together. So if we want to get together and work on the project, we'll just go find each other after class and head to the lab. Back to you, Lauren.
Thanks, Sienna. Go for it, Austin.
Thank you, Lauren. I am also on a team of 4, including myself. And luckily, my project, kind of the objectives that we had 4 parallel kind of work paths that we needed to get through. And so each of us kind of all took one that we wanted to work on and kept going through it. So when the COVID-19 thing kind of sent us all home, it didn't stop us too much. We did have to adjust to meeting online and stuff, but we were all able to continue to independently work on the tasks that we needed to get done. Back to you, Lauren.
Thanks, Austin. I also definitely worked with a team. I have one specific partner who's an undergraduate, but I've definitely leaned on all of the graduate students on the 3rd floor of Johnson. Now it is time for our second question. What were some other projects from previous years or other projects within your class? Let's start with Cameron.
Yeah, so like I mentioned earlier, civil engineering projects are super intensive in their scope a lot of the time. So for example, redesigning a school, you need information on the structures, and that plays into kind of how you design the parking lot, for example. And so in class, it's difficult to do, like in individual classes, it's difficult to do projects at the scope of what the capstone project is. And so we have done some design projects in those courses, but much more narrow in scope. For example, we designed a simple braced frame for an office building in one of our steel design classes. That allowed us to look at materials selection and kind of load path and just generally how you put together a steel structure design. And that's pretty typical for structures classes, but is more difficult to do for other classes within the civil engineering discipline. Back to you, Lauren.
Thanks, Cameron. Over to you, Amy.
Thank you, Lauren. Within mechanical engineering, the big underclassmen project is a class called ME 382, which is where you and a team of 3 other people will build a robot. And the robot has to complete a certain set of challenges. In the instance of my year, the robot needed to be able to complete an American Ninja Warrior style competition field. Then once you get up to your senior level classes, you have an opportunity to do one of 3 paths. The aerospace path, you can also do the motorized car path, and then you can also do a general path. I chose to do the aerospace path with NASA USLI. I've also worked within OSU AIAA, as I mentioned, for the past 3 years, this being my 4th year, doing things such as trying to figure out how to launch a rocket as far as possible with only Alka-Seltzer and water as propellants, doing things a lot with black powder and CO2 testing, also helping figure out how to build a glider that can roll up inside of an airframe that's approximately 6 inches in diameter, and then be launched up and then deploy at altitude, unfurl its wings, and then glide autonomously back to home. So those are the kind of projects that we work on in mechanical engineering. Back to you, Lauren.
Thanks, Amy. Go for it, Sienna.
So for the class that I was in, junior design, so we had a range of projects that we can choose from, or you can choose your own. There were music boxes and there were sumo robots. So 2 robots try to push each other out of the ring. And we also have stuff like energy related. So how can we, make a phone charger based on solar power and things like that. So this class, the junior design class, leads really nicely into our senior design class, which, you have even more options to choose from. Back to you, Lauren.
Thanks, Sienna. Now we have Austin.
Thank you, Lauren. Yeah, so within nuclear engineering, there's a wide variety of subfields. And this year we have a pretty cool mix of different projects. There's one group that's looking at shielding astronauts during a trip to Mars for NASA from space radiation. There's a group redesigning one of the current test facilities at Oregon State University to test a different phenomena. There's another group redesigning part of the Oregon State trigger reactor to be able to test different things. My group's looking into using Xenon 135 like I was talking about. There's a couple other students looking into some of the liquid sodium work that we have going on. There's a lot of cool stuff happening in the nuclear engineering department here at Oregon State. Back to you, Lauren.
Thank you. Within chemical engineering, you get to do senior plant design, which I'm definitely looking forward to. And there are lots of projects on things like elongating the health of organs, so how to preserve them for longer, or how to develop lateral flow tests and things like that. So there's lots of different stuff going on that you can get involved with. Our next question is, how did you all decide on engineering and specifically your majors? We'll start with Cameron.
Yeah, so growing up, I always really loved looking at maps, specifically maps of urban areas. And I love just kind of envisioning how the fabric of an urban area kind of works as a system to keep people alive and keep people happy. And ultimately, I ended up in civil engineering because engineering offers you the opportunity to solve problems. Actually going out and doing calculations that are going to change, the way that people live. And civil engineering is a really, really direct way of doing that, right? Because everybody interacts with infrastructure every day. And transportation, I think, is the most kind of direct and personal part of that, right? In order to get to anything that you're doing and get from one place to another, you're interacting with the transportation infrastructure and the transportation system. So that's how I ultimately landed on that focus. And my internship experience while I've been at Oregon State has kind of helped to solidify that, because I found that I've actually enjoyed doing some of the problem solving that's associated with it, which makes the day-to-day job match up with the romantic ideal of it. Back to you, Lauren.
Thank you, Cameron. We'll go over to Amy.
Thank you, Lauren. I chose engineering because in 5th grade I watched a movie called Apollo 13, and there's a scene on there where a man named Gene Kranz, who's the flight director, was going through with all of his flight controllers doing the checkoff, and I looked at that movie and I said, I want to be Gene Kranz when I grow up. I want to be a NASA flight director. And so I pursued engineering, and I found that I had, out of all the engineering fields, a knack for mechanical engineering more so, and that's why I chose mechanical engineering. Thank you, and back to you, Lauren.
Thanks, Amy. We'll go over to Sienna.
Thank you. So for me, it's a little different. I really never ever thought that I would choose engineering because, growing up, none of my parents went to college, and to be honest, I never really liked math that much. But this sounds a little like a little cliche, but I knew that I wanted to do something good, and I wanted to create something that's good for the next generation. And so I started looking into engineering, and with electrical engineering, I can work everything from renewable energy to what I have mentioned before, prosthetics, and it's also the perfect blend of hardware and software. So that's why I chose electrical and computer engineering. Back to you, Lauren.
Thank you, Sienna. We'll head over to Austin.
Thank you, Lauren. I have always been interested in nuclear power and nuclear engineering, and couldn't tell you why, but since I was maybe 12 or 13, I knew I wanted to be a nuclear engineer. And so that was just kind of the path I went down, and sticking to it. Back to you, Lauren.
Thanks, Austin. I definitely enjoyed chemistry in high school, but I didn't really know about engineering until my chemistry teacher told me about it. So I Googled it, and it seemed like a great way to have a little more hands-on work while still getting to enjoy some of that chemistry and math that I liked in high school. All right, our next question is, what was the first step in your projects, and how did you begin each experiment? We'll start with Cameron.
Yeah, like I think most of us have mentioned at least once, none of these projects happen in a void. Like we're all working in groups, and if the prompt is build a school, it's kind of a big question to figure out where you're going to start, right? And so the first step in probably most of our projects, but specifically for my project, was just defining the scope, and more specifically defining the scope for each area. I mentioned each of my teammates had a different specialization. And really, really important for us was to kind of break up who was going to do what work, and what that even entailed, right? So looking at what the stakeholders want out of a school, what is a school, and kind of what are the steps that we're going to need to take to get there. Defining those was the first step for us. All right, back to you, Lauren.
Thanks, Cameron. Over to you, Amy.
Thank you, Lauren. The first step for my team, and ours was a large team, particularly with the capstone members, was dividing up who exactly wanted to do what portion of the project. So we had aerodynamics and recovery, we had structures and propulsion, and then we also had payload. And we also need to figure out who wanted to do which of the non-technical roles. Who wants to do budget and finance, who wants to focus on STEM engagement, those kinds of things. And then we had to submit a proposal to NASA for exactly what it was that we were going to try to complete and construct in order to complete all the challenges that they set before us. So that was how we got started. Back to you, Lauren.
Thanks, Amy. Go for it, Sienna.
Yeah, I'll have to agree with Cameron there. So for my project, the first thing that we did was to define the scope of the project. So take again the robotic arm as an example. So for example, when the robotic arm holds a pen, because of the weight of the pen, it might bend down, right? So how many degrees of bending down is acceptable? Or whenever a user flexes their arm, how many seconds of delay is acceptable from your initial flex to the robotic arm moving. So by defining those scopes, defining these requirements very clearly at the beginning of a project can save you a lot of time and energy and money down the line. Thank you. Back to you, Lauren.
Thanks, Sienna. Go for it, Austin.
Thank you, Lauren. So like Cameron and Sienna were talking about, the first step to any project is defining the scope and exactly what you need to do. But a more important thing that kind of happens along there, maybe not more important, but just as important, is what we call in research literature review, which is horribly boring. And you look through tons of research papers, you look online, you look through books, you ask people in the field, and you try to see if anyone has ever done anything remotely close to what you're trying to do now. And you read all of it, and you just gather all the information and put it in your head. And hopefully by doing that, you'll at least know where you're going, know how much work you need to do, and how much work's already been done for you. If you can find someone that's already done what you're doing, that's sometimes awesome, because then you don't have to do that work. So that literature review is a really important part and is a giant chunk of our final report. Thank you. Back to you, Lauren.
Thanks, Austin. I also had to start with a literature review, which was not my favorite part. I had to spend a lot of time Googling the words that I could develop an understanding, but then we ended up not wasting as much time or money because we had a basis of understanding of what we were trying to do. So it was very beneficial in the end. Our next question is, there's a lot of interest in robotics. So you want to know how to get involved in robotics, and you should know that it's not an undergraduate degree program here, but it is a graduate degree program, which means that there is a ton of research out there for you to join. I know people who got involved as early as their second term at OSU, and there's lots of programs there specifically developed to engage first and second year students and getting involved with research. And since there is so much in robotics, oftentimes people steer that direction. You don't have to be in a specific major to get involved with robotics. It's more about having a genuine interest in it. And there's also OSU Robotics Club, which is a great way to get involved. They have an awesome Mars rover team that goes to competitions that are sponsored by NASA. So it's a great way to meet people from NASA as well. There's all sorts of different ways to get involved with research, especially robotics specific research, if that's what you're interested in. Our next question is, have you been on a path towards these projects since your first year at OSU? And how did you know if it was going to be too hard? We'll start with Cameron.
Yeah, so I'm sure this is the case for many of the other engineering majors, but when I showed up for civil engineering, I was surprised just how broad the coursework was going to be for the next 4 years. You get options ranging from, like I said, from structures to water resources, to geotechnical engineering, to surveying, and all the way over to transportation. And so, starting my freshman year, I had no idea that I'd be working on a transportation project now, 4 years later. But through getting involved in extracurricular activities, specifically with the Institute of Transportation Engineers on campus, I really got to hone my focus within my major and kind of know that when it came time for my capstone design project, I would be working on a transportation component of it. So really it was that exploration through that extracurricular club that helped to focus and helped to make me, helped me make the selection for what I would ultimately do on this project. Back to you, Lauren.
Thanks, Cameron. Go for it, Amy.
Thank you, Lauren. I actually have been on basically the same path since I set foot on campus 4 years ago back in September. I knew that I really wanted to do something within aerospace, and so as soon as I possibly could, I joined OSU AIAA and jumped in feet first into the rocketry teams. Also, with the question about how do you know if things are going to be too hard, there's definitely a question with that within our aerospace club because some of it is literal rocket science, and that's a lot to amount to sometimes. But a lot of it is trying to just kind of remember within yourself that you are actually quite a very capable person if you just are willing to kind of sit down and buckle down and really try to punch through it and understand and learn. Also, it's a community thing, as you've all heard from all of us. We are not doing this alone, so if there are things that we don't quite understand, or if there's a challenge that we're just beating our head against a wall and we can't figure it out, we have people that we can rely on and ask people about, hey, do you know about this thing, or what's your input on this? Because I can't figure it out for the life of me. So that's how we typically tend to tackle challenges, particularly the ones that seem really insurmountable. Thank you. Back to you, Lauren.
Thanks, Amy. Over to you, Sienna.
Thank you. So for me, like what I have mentioned earlier, because I haven't had any experiences with engineering before I came to OSU, so I've definitely explored many paths and just was basically all over the place. But with each new thing that I learn about, all my attention gets shifted to that, and that's okay because I get to explore so many aspects of engineering, or specifically within electrical and computer engineering. With the question, how do we know if it's gonna be too hard? That's definitely something that I struggled with because I can definitely be over ambitious, and so my teammates or my professors would tell me, whoa, like hold on a second, let's take a look at this, define the scope, right, of your project, and then let's see what our next step should be. Thank you. Back to you, Lauren.
Thanks, Sienna. Go for it, Austin.
Thank you, Lauren. So my very first year here, I had no idea even what I wanted to do, like remotely after school or for a senior project or anything, but getting involved with research on campus, I was lucky enough to get a senior project that was very closely related to research I was already doing, which kind of feels like cheating sometimes, but it can be pretty fun. Nuclear engineering can be exceptionally difficult sometimes, and some of the projects that you get as a senior project can be very, very broad and very challenging, and so it is always a fear that it's going to be too hard. But the faculty are great and they want you to succeed, and so they will adjust the project as needed. They will let you know, like, hey, this would be cool if you can do it, but don't worry if you can't. And with the whole COVID-19 shutdown, both the professor teaching the class and my project advisor sat down with my team and we readjusted the project scope so that it was going to be something that we could get done in the time that we had under the conditions that we had. We weren't able to do physical experiments anymore, so we had to shift to only getting the modeling done and kind of adjusting for, we weren't going to be able to put in the same amount of effort as we could if we were on campus. So we had to tone back everything that we wanted to get done and readjust to what was actually going to be possible. Thank you. Back to you, Lauren.
Thanks, Austin. I got very lucky, and within chemical, biological, and environmental engineering, there is a program you can apply to called the Johnson Internship Program that gives you an internship for your first summer here for about 30 students to go do research at OSU or U of O or PSU or OHSU. And it is super fun. And I got placed with my current professor. And so I was not on my current project, but I got to learn a little bit about her lab work. And it was a great chance to get started. And in terms of it being too hard, there are just layers upon layers of resources for you. You're definitely not in it alone. Not only do you have partners, but your professor wants you to succeed. So they're there to answer any questions that you might have. All right. So next we have a couple questions for you, Amy. First, how competitive is your major within mechanical engineering? And how do you join your club? Can you join in your first year? Do you need previous experience? Go for it, Amy.
So at least from my perspective, mechanical engineering isn't super duper competitive. The first couple of years, you do have some very challenging courses that kind of help you figure out if mechanical engineering is really what you want to do with your time in your life. And then after you get past those, everybody's just kind of in it together and just trying to get through all the coursework. And so you really kind of congeal as a family as opposed to trying to bring each other down. You're trying to bring each other up. As for joining OSU and OSU AAA, you can join freshman year straight out of the gate if you really want to. Come and join through, or you can sign up for our mailing list, and you can sign up on the Student Leadership Institute website through our website, which is osuaiaa.com, so AIAA.com. And you don't need any previous experience. If you have no experience, that's perfectly fine. We will teach you everything that you need to know, and you will teach us what we need to know, I guess. So that's where we stand on that. Please, if this interests you, come join us. Thank you. Back to you, Lauren.
Thank you so much, Amy. We have time for just one last question. What are all of your plans for after college? We'll start with Cameron.
Yeah, so like I mentioned a couple times, I was lucky enough to get some internships with some transportation engineering firms, and I'm really excited to be joining another one of them right out of the gate here after graduation. Planning on working for them for a year and then heading back for a graduate degree is the hope right now. Yeah, back to you, Lauren.
Thank you, Cameron. Go for it, Amy.
Thank you, Lauren. Ideally, after I graduate from college, I would like to go work within the aerospace industry, preferably with NASA, as my ultimate goal is to be a flight director for NASA, and hopefully work my way up that ladder to be a flight director. Thank you, Lauren. Back to you.
Thank you, Amy. Go for it, Sienna.
For after college, I don't know. I have no idea what I want to do, and I think that is perfectly okay because there are just so many exciting things within engineering. How should I decide, right? But I'm on my first internship right now, and I have another internship lined up next year. So hopefully that'll get me to experience many different things, and hopefully that can help me to decide a little bit. And there's also always the option of going to graduate school as well. Yeah, thank you. Back to you, Lauren.
Thank you so much, Sienna. Now we have Austin.
Thank you, Lauren. I actually love the Oregon State University nuclear engineering program so much. I'm staying to do my master's after I graduate in the spring. Thank you. Back to you, Lauren.
Congratulations, Austin. I'm also not sure what I'll do when I graduate. I have an internship which should hopefully help me decide, but ideally I'll be working towards the goal of providing access to clean water. So thank you so much to our panel, and thank you so much for all of the great questions for our panel. I hope that it helps those of you watching today envision yourself doing the kinds of projects that you've heard about.